Dear students, today we'll see the topic three-phase full and half controlled rectifier fed, separately excited and DC series motor drives. In the previous class, we have discussed on single-phase half controlled rectifier fed separately excited DC motor drive, where we have solved problems to find out the various parameters of the DC drive. So today we will move on to three-phase drives. So at the end of this session, you should be able to determine the firing angle, speed, back EMF of three-phase full and half control separately excited DC motor drive. In this session, we'll mainly concentrate on the operations of three-phase drive. In the next class, we'll solve the numerical problems. Three-phase converters are normally used for high power applications from about 15 kilowatts to several thousand kilowatts. Whenever large power rated motor is there, which is driving the mechanical load, maybe in industrial applications, in that case, three-phase supply is converted to DC, and we'll move on to what is called as three-phase DC drives. The output voltage of a three-phase converter has less ripple as compared to single-phase converter. This makes it advantage to uh, to have high efficiency and also smooth current. That means current is almost continuous, and hence three-phase DC drives are preferred over single-phase DC drives for large power applications. Coming to three-phase half-controlled converter drive. Let us first consider half-wave converter circuit connected to a DC motor. So here you can see here we require three switches or three thyristors connected to each line, and their common cathode terminal is connected to the plus terminal of the armature circuit. The other end of the armature is connected to the neutral point of the supply. If, for example, the phase voltage is given are Vm sin omega t, then 1 second. If the phase voltage given are Vm sin omega t, Vm sin omega t minus 120 and Vm sin omega t minus 240, then these phase voltage waveforms can be represented like this: VAN, VBN, VCN with a phase angle difference of 120 degrees. Now, for the device to operate, if let us say T1 is to be switched on, its anode voltage should be greater than the anode voltages of other two devices, and that is possible when VAN is greater than VBN and VCN. And during this portion, VAN is greater than VBN and VCN. So this is the duration during which the thyristor T1 can be turned on. Similarly, this range will be the one where the second thyristor can be turned on. And here, this is the duration during which the third thyristor can be turned on. So you can see here, this crossover points are located at 120 degrees apart. So when T1 is triggered at this crossover point, it can conduct for 120 degrees. Next crossover point, we can trigger T2. So you can see here, each thyristor will be conducting for 120 degrees. If the device is turned on at this crossover point itself, then we say that the delay angle is 0. That means this crossover point is taken as the reference point. From this reference point, alpha is measured. Okay. So if, for example, we give some delay and switch on the device at some value, let us say I'm turning on here, then T1 will be conducting up to 120 degrees up to this, and then T2 will start, and then T3 will start like this. Next T1 takes over, T1 takes over like this. So with that, what we can see here is this 30 degrees, 5 by 6 point or 30 degrees point is taken as a reference point. From there, there is a delay angle of alpha. From that alpha, each thyristor conducts for 120 degrees. So there will be three output pulses. There will be three output pulses like this in the output or load voltage for duration of one cycle of input supply. So if the input supply completes one cycle, the output voltage will be having the three voltage ripples like this. Normally for a three-phase system, a motor size is very large, which has large inductance, or in addition an inductor can be added here. So therefore current is almost continuous. And you can see here, this is IT1, current through the thyristor 1. So it is turned on at 30 degrees plus alpha, conducts for 120 degrees, and then turns off. And then turns on. Okay. So for this type of output to load voltage, what will be the average output voltage for this waveform? So that is this one, E average. So you can see here V naught average is integral of Vm sin omega t from where to where? From 30 degrees alpha to 30 degrees plus alpha plus 120, and divided by 120 degrees width, that is 2 pi by 3. So if you solve, we'll get V naught average is 3 root 3 Vm by 2 pi into cos alpha. And you can also observe here that depending on the current value, the motor can operate either in the first or in the fourth quadrant. So that means forward motoring operation or reverse regenerative braking operation can be obtained from three-phase off controlled converter connected to a DC motor. So now come to a three-phase full wave converter. Three-phase full wave converter with half control. In this case, now let us consider bridge circuit, full wave rectifier bridge circuit. There will be six devices, out of which three are controlled switches and three are diodes or uncontrolled devices. So now the bridge connection is shown here. The converter or bridge connection. Input is AC and output is DC. Okay, let the average output voltage from this converter be VA, and this is connected to the motor which has LE and RA as internal, or external inductance can be connected, and freewheeling diode is connected. As it is a separately excited DC motor, the field winding is supplied from a separate supply of constant value. So now uh, a three-phase semi-converter is a single quadrant drive, because as there is a freewheeling diode, the negative current cannot flow, and hence all the power or energy stored in inductor is dissipated through the freewheeling diode. So it operates only in the first quadrant. So in that case, the average output voltage equation will become V naught average is 3 root 3 Vm by 2 pi, 3 root 3 Vm by 2 pi into 1 plus cos alpha, 3 root 3 Vm by 2 pi into 1 plus cos alpha. So the average current is IA average is equal to VA average minus EA divided by RA. VA average minus, this is back EMF. Okay, from the circuit here you can write this one. Okay. IA average is equal to VA average minus EA divided by RA, and that is equal to 3 root 3 Vm by 2 pi RA into 1 plus cos alpha minus EA by RA. So we'll solve the numerical problems in the next class. So coming to this three-phase full wave fully controlled converter drive. In this case, all the devices are the SCRs. So if the inductance is very large, then we can have continuous operation. And for continuous operation, VA average output voltage of the fully controlled converter is given by 3 root 3 Vm by pi into cos alpha, 3 root 3 Vm by pi into cos alpha. And the average armature current IA average is VA average minus EA by RA, and that is nothing but 3 root 3 Vm by pi RA into cos alpha minus EA by RA. For discontinuous operation, the armature voltage has average value. For discontinuous operation, it conducts for alpha to alpha plus 30 degrees. So we have 3 root 3 Vm by pi, 3 root 3 Vm by pi into cos alpha plus 30 minus cos alpha plus 90 degrees. Okay. Based on that, you can write down the average voltage equation. This is general common, and this is the motor torque in terms of current and in terms of speed. We'll discuss this problem in the next class. So we have seen here what are the equations of average output voltage of a three-phase half-wave rectifier, three-phase half-controlled converter, and three-phase full-controlled converter. And when this type of rectifier or converter is used for speed control of the motor, uh, what is the quadrants of operation that we have seen, and the equations of back EMF from top, quadrants of operation, determine the determine the firing angle, speed, back EMF of three-phase full and half controlled DC motor drive. So, dear students, you should be able to explain the operation of three-phase drives, and you should be able to find the firing angles, speed, and back EMF of this three-phase drive. So, these are the numerical terms given. We'll discuss in the next class. So, refer these topics 5.1 to and 5.3 of GKLP, and go through the examples 5.17, solve the problem there, and based on that, you try to solve the exercise problem 5.43 and 5.44. Okay. Thank you, students.